Hi everyone. In today's lecture, we'll learn about some advanced version of searching. Advanced, what does that I mean is, till now whatever we have learned, we have given a problem. We are doing the searching. Fine, but this time, along with the problem, we'll also have some intuition or heuristic. We'll try to incorporate in a solution and see whether it is doing better than the uninformed search, or with the no information we'll try to see. So till this one we have read about this algorithm: breadth first search, uniform curse search, depth first, and iterative deepening, bidirectional search, and all those things we have discussed in our lectures. So this has been compared with the whether they are complete. Complete means whether it is able to halt to a solution or not, if it exists. Time, space, and optimal. These four things we have compared. Now, what was the problem with this searching algorithm? They were good. They were finding some solution, but the problem was the time was taking too much, because we don't have any information. We are trying to explore everything there. Can we put some additional information? Can we put extra information with that and see whether it's making difference or not? Because in real life, whenever you do something, it's very less likely we start from scratch until unless some exception scenario. We have some background, and that we try to exploit that information in a problem setting. So here also, rather than doing blind search, right? Can we put a guidance there? Can we put heuristics there? Can we put intuition there? And those are terms as a informed search. So rather than uninformed search, we'll have the information, and that information we are trying to exploit. How we are going to exploit that, I'm going to discuss in next slides. But this is the idea. Idea is that you don't explore everything. I'll give you some intuition, some heuristic, some idea, and you try to go in that path. So this is what we have. So it is, be smart about what paths you are going to try. For example, this is the green node. This is the green node you have, and you are trying to this is the start node. You want to go to the red node, which is the goal node. How will you go? So what option we have? We have to expand either n1 first node, n2, or n3. But you can see the n3 branch, we can see the solution, but how to encode that information to a computer? If you have some additional information, whatever the path you are looking, it is more than 3. Let's say path more than some number. So this one, first two are not satisfying that property, and you can see the third branch is going in that way. So third branch and that too, but so you can explore that branch first. So try to understand what I'm saying. Fine, along with the problem, I'll give you extra information. So how you're going to use that extra information? There are two ways. What are two ways? First way is that if I'll give the information, you are quite sure which path to explore. I'll give you that this path may go to the solution. Not exactly I'll give you, but I'll say that might lead to. So you're going to explore that path. This is one information. Another path information I can give you, that this solution is never going to work. Then you are not going to try that solution. So you're pruning that part. So that this information will be utilized in these two ways. So till then we have read about the blind search. BFS, DFS, whatever you have read, they were the blind search. No information has been given. Now from the blind search we are going to informed search. So what we'll have? We have this extra information. For each node there would be some evolution function. For each node there will be some evolution measure. Some number would be there, and that would be measured by evolution function. what it says, that evaluation function, which will say the estimate cost to goal. So it says that node of a, let's say, tree, and its cost its estimation evolution is, let's say, 100. What does that mean? What does that signify? It signifies that from that node to reach to the goal node, you are going to, most likely you're going to get 100 rupees or 100 something unit of cost. So it is giving you the information that in what future direction you are going, what is the likelihood of that path to reach to the goal, or how good is the path. That would be more appropriate, I should say. If that cost is too high, you are quite understood that this path is going to cost too much, so why should I go to that path if some alternative exists and the cost is less? So I'll try to go in that path rather than going in this path. So I'll explain again. There are two terms, evaluation function and evaluation cost, that you are going to assign to the each node. Evaluation function is the information, you are giving. What information you are giving? You are taking a node, you are saying from that node to goal node, what is the likelihood or how much it is going to cost from that node to goal node. That information I'm putting at each node. So this is known as evaluation function, or you can call it as a heuristic function. From that node to reach to the goal node, what cost you are going to incur. So that information I am associating with the each node. So this is the information I am giving, right? So for example, from I am in Patna, and from there I have to go to a path ABC. So I'm seeing Google Map and I can see 4 paths are there, but I can see on 2 paths there is so much traffic. I haven't explored that part, but this information I have got it from the Google Map. Then I'm quite sure I'm not going to explore those 2 paths. I'll explore, leave it, and I have only options in other 2s, which should I go. So this extra information is, it's being called as informed search or heuristic based search. What is heuristic here? Heuristic is the traffic information that I, got it with the Google Map. So this is the difference between non-informed search and informed search. You have information here. Now coming to the first kind of informed search, which is best first search. What it says that you are at the, let's say, position P, and you have 3 options, either to select N1, N2 and N3. So you just take the best first. You evaluate evaluation function for all 3 options, N1, N2 and N3, and check which one is more desirable to go from that node to goal node. Evaluation function you computed, and check whose desirability is more towards the goal, and you select the node. This is the best first search, right? So how will do implementation? It's pretty simple. It is saying you have whatever the option you have, you take the node, you take the path whose probability, or if I say evaluation function is quite good. Quite good means from that node to goal node it's more likely to reach, and that too with some optimal cost. So this is known as best first search. So for each node there would be some term associated, and that term says from that node to goal node how much it costs, and you select the node which is costing you less. So cost, it sometimes it's not evaluation always needs to be minimized. If it is something related with the cost or error, that needs to be minimized, but if it is something related with the reward, it needs to be maximized. So this is the difference. Evaluation function is not associated with the minimum or maximum. So these terms, please take it carefully. Now see this example. So this is the map, and nodes are the places, and the distance is like a step cost in kilometer. Fine. You are at some node, right? So let's say you are at some node here. We are here, and from here we have to go somewhere. So this edge cost is saying from that node to going to next node how much it is going to cost. If you will have only this information, you are going to see which is costing you less, and it's more reachable. It's more going towards the goal node. So we had till now we have understood and discussed about the uniform search, which were DFS, BFS and all. So we have BFS, breadth first one. So we are also doing their best first. What was the criteria there? The criteria was we'll go each depth at once, let's say depth 1, and then we explore all the nodes. So here the priority was depth, so we'll go step wise, depth wise. So this function f of n was, our priority was depth, so that's what we're calling it as a f of n was depth. In uniform cost search, it was also kind of base first, but idea was what you are choosing. In uniform cost, we are seeing cost there, some of the edges cost from start to n. So we are saying from starting node to nth node how you are reaching there. So that cost we were considering there. It is also here, it is termed as g of n. So you are at, let's say, nth node. So how you have reached to nth node? You started with some start node, right? And you went to some next node, some next node and some next node. So from that start node to node n, how much cost it has occurred. So this is known as this, and this is also kind of uniform cost search is inform search, and the information is only that information here. Now what is greedy base first search? It says evolution function will be equivalent to h of n, heuristic. What is the heuristic? It says estimate cost of a goal, from nth node to goal node. You have three options, n1, n2 and n3. You select saying always n3. Why? Because for n3 the heuristic cost is 200. What does that mean? It means that from n3 to reach to the goal it is going to cost 200. Why should not select n1 and n2? Because the heuristic cost is 300 and 400 for n1 and n2 respectively. So we are going towards, we are selecting a node from where reaching to the goal is more probable, not I should say in less cost, right? So that's why we expanded n3 compared to n1 and n2, right? So it is always greedy. It is saying you are at any node, okay, good, but from that node to going to next node, only criteria is that you select the node which is from there you go to the goal, the cost is minimum. So for this example, what would be the h of n? What would be the heuristic here? Heuristic extra information. Extra information would be the distance. Just if I say graphical distance or the straight line distance between from let's say Cebu to Lassi I want to go. So I should go forward direction Cebu to these nodes rather than going backward. I cannot go backward. If I'll go backward, I have to again come to this stay Cebu or Tismania, and then have to go further. So if I'll go backward, what will happen if the distance, if I say let's say Cartesian distance between these two nodes where I'll reach, and from there where I have to go. So if I'll see the Cartesian distance, that would become max more compared to previous what it was. Say I'll say, oh that's not good. Where I was, the distance was 100 kilometer, but now I took a action and now distance become 105. It happens in real life also. Now you follow some Google map and you see you put some target and you started doing that, cool, But after some time you see you're following the path and distance is becoming increasing. Initially it was 3 kilometer, now it become 3 and 200 meters. So you're saying, oh, I'm not going in right direction, I'm following some wrong thing. So I'll again recenter and see which is the correct path. In many cases I used to ask, which path should I follow? So here it is the same way that heuristic is giving you the information what action you have taken. Now distance, whether distance has increased. Yes, it is increased, means you are going in right direction. That direction you shouldn't follow. If distance has been reduced, then you can think, okay, I'm going in right direction. So this is the kind of heuristic you can put it here. Greedy based first search expands the node that appears to be closest to goal. Exactly. So this term please try to understand thoroughly. It says what? It says that you are at the nth node, you have an option to go to M and P. Where I'll go? You expand to a node which is very near to goal G, let's say, if G is the goal node. So you take M and P, any of it, either M or N or P, but make sure where you are going, whether it's M or N or P, from there distance to the goal is way lesser than other two, right? So this is what it is greedy for. Greedy for means I'm going to select action, and which is from where it's more likely to reach to the goal, more probable. Not probability, I should term, I'm again using this term, cost I should say. So from there reaching to the goal is giving me less cost. Now let's understand some property of greedy based first search. Whether it is complete, what does that mean? It means that if there would be solution and I'll run the algorithm, is it sure that every time it will terminate to a solution? This is the complete definition. No, greedy based first search may not be reach always to a solution. Why so? Because it falls in loops many times. What does it mean? Why it is falling in loop? Let's go to our previous example. We are at this position, let's say, lossy. What two options we have? Either go forward, which is Nimat, or go backward, which is base tool. The cost, if you see, which is 87.92, which one is you are going to select? You are going to select 87. You are going to Nemat. Okay, now we are in Nemat. From Nemat, what option we have? We have only one option. What is this? Lossy. I came back to lossy. Now what to do? If I select, I'll see again I have two options, Nemat or Veshul. What I'll do, I'll take the minimum one. I'll go to the number. So this is creating a loop, right? So this is the problem has been mentioned. No, it will not every time reach to a solution. Sometime it will fall in loop, and that's why it is not complete. What about time? How much time it is taking? So it is taking beekeeper M, where B is what? Branching factor. What is M? M is the space. How much is taking space? It is taking same as the time, which is order of beekeeper M. Why it is taking so? Because we need to keep track of all nodes in the memory that we have here. It's optimal or not? Obviously no. Why? Because if it is not complete, how it can be optimal? It is not complete. There are few situations where it is not able to find the solution, because it may fall in loop. So obviously it will not be optimal. Now coming to so what we have read till now. We have understood what is informed search, how it is different from uninformed search, what is greedy based first search, Now an advanced algorithm is A star. So it is saying, till now whatever you have done, okay, good, but along with that you should also follow one more important thing. What it is, avoid expanding the paths that are already expansive. It is saying your previous algorithm were doing one not mistake, you are doing one thing only. What is that? It's saying your previous algorithm, every time it is selecting a node from where you are to the goal node, you are going, easily. What was the problem there? Yes, there was a problem. What was the problem? Problem was that you are going forward only. You are thinking about that from that node to goal node, how, which is reachability. But how you have come to that node, you should also consider that one as well, right? Because you have followed very costlier path, and from there you are going to goal. It's very easy, that's okay. But the previous path which you have followed from start node coming to the nth node, which is very costly, if I'll do the sum for taking the path from source to target, the number would be very high, right? So it is saying you should also consider this factor from start node to the goal node, how we are reaching, and avoid expanding the path that are already expensive. And you should not expand, you should not go in the path, you should not expand which is already costly to reach, right, to nth node. So how evolution function look like? Evolution function would look like something to that, f of n, which is equivalent to g of n plus h of n. What is g of n? What is h of n? G of n is cost so far to reach n. So you are at the nth node and you are computing evolution function for nth node. That's cool. So which is equivalent to g of n plus h of n, and g of n says to reach the nth node from source, how much cost you have occurred. That's okay. I put it g of n. Now from that node to reaching to the goal node, what is the cost, which is here h of n, estimated cost from n to goal, and f of n is sum of these two factors, which is equivalent to estimated total cost of path through n to goal. Let's understand thoroughly. It says that evolution function of nth node n will be equivalent to g of n plus h of n. What is g of n? G of n is from start node to nth node, how much cost you are bearing. Okay, we consider that factor, plus from that node to goal node, what cost it is going to occur, right? So this sum is representing how good evolution function of nth node. So finally f of n is computing total cost of the path through nth node to goal. Coming back to our running example, so this is the graph and now we are adding some terms, some numbers associated with each places, which is evolution function. So now from Arad we have to go where this is the Arad, and we have three options. Jerian, this what is the Timonsnia or what, it is not clear. Another one is the Cebu, right? Which one should I expand? I don't know. Let's see. For Cebu, so for Cebu, let me see what is the evolution function. Evolution function for Cebu, if you can see here, it is 253. So from Arad to Cebu it's 140, and for Cebu to goal it's a 250. So sum would be 140 plus 250, 253, which is equivalent to 993. For RR to this one path, it is 118 plus what is the cost of this node, which is 118 plus this cost of this node is 329. So 118 plus 329, which is 447. Similarly for the other one, JDN. So 75 plus something, it did it. So which one should I expand? Which has the minimum one. So this 393 one is the okay one, right? So we are going to expand Cebu. So hope you understood it. Let's again explain with some real life example. So what was the motivation why we were doing so? Currently I am in Patna, and I and my friend wish to reach to, let's say, Rishikesh. Fine, I took train, I reached Rishikesh. He also, reached Rishikesh, but he reached Rishikesh in only 7 hours. But he has not followed my path. So can we say that whatever path he has followed is optimal? Maybe, may not be. Why? Because that time he was in Delhi, and from Delhi he took some service and he reached to Rishikesh, which took 7 hours. But in order to reach from Patna to Delhi, he took 20 hours. So total cost is 20 hours plus the 7 hours, which is 24, 7 hours. For me it is only 15 hours. So mine was better compared to what path he has followed, right? So that's why we are also considering it's not about from a node to reaching to the goal, but how you have reached the node. Have you reached the node with the very costlier path from start node, or it is that not costlier? So from start node to nth node, that's why we are also considering this cost. In earlier problem we were only considering from that node to reachability to the goal node, how likely or how if is it taking minimum one, right? So here we are considering both the parts. This is the difference between these two. I think now you are able to get the idea why we are considering both these factors. Now come to some important concepts. Admissible heuristic. What is this term? Admissible heuristic. You understood. Heuristic means extra information, or about the problem and or intelligence you have that you are going to use it in your problem solving technique. This is known as heuristic. Okay, cool. But what is admissible here? A heuristic would be admissible. When it will be admissible? If it follows this equation. What is the equation? It says there is a heuristic h of n, and if it is less than h star of n, if I know a heuristic which is optimal, and whatever the heuristic you are giving me, if it is always less than an equivalent, then I can say this heuristic is admissible. It means that it is always being optimistic. It is always saying a cost which is either equivalent to the gold one or the optimal one or less than that. It is never overestimating, saying okay, from nth node you want to reach goal, it is 200. So in reality, which is S star n, it may be 201, it may be 250. That's okay, but it cannot be 150. If it would be 150 means you are saying 200, you are overestimating, and it contradicts with the admissible heuristic. It is saying whatever cost you are going to say, that's okay, say, but that make sure that cost is always less than or equivalent to what is in reality. It never overestimates. It always optimistic about the cost. Okay. What about the running example? What heuristic should we take? So you can take it as what heuristic would be, never overestimate the actual road distance. There is one more important concept associated with the heuristic, which is consistent. You understood what is the admissible? Admissible says you are assigning h of n to each node. Fine, assign. What is it? It represent that from that node reaching to the goal node, how much cost it is taking. Is it admissible? I'll do a checking and say whether it's admissible. What checking? Checking would be for each node whatever the cost it will be associated. If it is 200, I'll see actually what is happening from that node to reaching to the goal in the optimal path. Is it taking more or not less? Oh, I calculated it is 150, but my function says 180 or 200, let's say. Then no, it is contradicting with reality. I said it is going to take only 150, but it is saying 200. It is overestimating. So this not going to be a admissible heuristic. Admissible heuristic definition says that whatever estimation it is doing for a node to reach to the goal node, it is always less than or equivalent to the function, that optimal one. Cool. Now coming to the consistent heuristic. So I think it is clear till there what is this admissible one. We'll now talk about consistent heuristic. H of n is there. I'll say H of n is consistent if it follows this equation. What is the equation? It says, you see this figure and understand. There are two nodes, n dash, and G is the node which is the goal node. From n there are two paths exist to reach to the goal. One is go to n dash, and from n dash go to G. From n you can directly go to G. So for n I'll see what is h of n, what is the heuristic function which is saying from n to hn how much cost it is going to offer. So I calculated it, and which is h of n, let's say. Another path let's explore, which is saying for going n to n dash you are going to cos c of n of you are taking an action A and you are going to a dash n dash and cos is c. Okay, fine. If I reach to n dash, I'll see for that n dash what is price or the evaluation function, and not evaluation function I should call it. It's called heuristic for that node to goal node how I'm going to reach, and that is the value is associated h of n dash. So it says that h of n, this which is reaching directly rather than going in path hops, which is always less than or equivalent to the other path which is going to another node and then from that node to goal node. This is the definition of consistent heuristic. If it follows, then you can say yes, the heuristic is consistent. Okay, so there is a very popular theorem which says that every consistent heuristic is also admissible. Means if consistent heuristic are superset of for what? For admissible heuristic. If I say this heuristic is consistent, then you can implicitly understand that yes, it is also admissible. Now let's understand properties of A star. So our 4 attributes that we always investigate. Complete. What does that mean? It means, is it complete? Means every time if there is this solution, will it find out the solution? Yes, it is. It is complete. If there will be solution, then it will be able to find out the solution. But there is a constraint. What is the constraint? It says unless there are infinitely many nodes, there should not be very large number of nodes with this function, where f of a is less than f of c. Time it is going to take exponential time. Space, it needs to track of all the nodes, right? Space will also be high. Optimality, yes, it is optimal. So if you saw in the previous slide, it has to track all the nodes. In order to track all the nodes, memory, we need a very large. So what we can do similar to whatever we had done earlier. We can do iterative deepening. So we can fix some limit and we go to that depth, and if it doesn't solution get there, we can double it or something like that, and we do another part of searching. So that we can associate it here. We can put this iterative deepening with A star. If I say H2 and H1 are two heuristic and say H2 dominates H1, what does that mean? It means that if I'll have the heuristic function H2, which is saying from reaching from N node to the goal node, what is the cost? If it is always greater than another heuristic, which is saying for reaching from N to goal, what is the cost? If this satisfies, then say H2 dominates H1, means always the cost for that reaching to the goal node from that node is greater than or equivalent to H1 of N. Now let's see these numbers and we're able to guess it why we are going to A star. So with D equals to 12, deepening depth, it is given 12. What IDS algorithm will do, how many nodes it will expand. This number of nodes too high. What will do H1, what A star will do, it will only expand with H1, some heuristic is 2 to 7, which H2 very less number of nodes, 73. So with D equals to 12, you can see this number is very high. If I increase the D, if I just double it, then it will be too much. Too many nodes needs to be expanded. What is the scenario with A star 1? If you follow H1 heuristic, then you will be able to do something 39,000. If I'll do H2, then it's only 1641 nodes needs to be expanded before reaching to the solution. So you can see the difference here, why we come from uninformed search to informed search, because the number and difference is huge. Where here you can see 36 lakh to 227 nodes, so much of difference, right? So now we are okay with it. We understood what is the dominance, we understood memory problem. So now come to this one. So what we have learned, we started why uninformed search is not enough, what to do, give some extra information, how to incorporate with HFN. What is HFN? Heuristic. Is it HFN enough? No. Every time you cannot be greedy, you cannot only consider that from node how much you are going to the goal node, but you should also consider if you are at the nth node, how you have been reached. If the path is very tricky, then you are not going to follow every time, right? Although from n reaching to the goal it is costing very less, but how will you reach to n? You cannot reach every time because the cost is very high. So that's why there is another component, G of n. So now how our A star look like? A star f of n is equivalent to G of n plus f h of n. That's cool. What is G of n? G of n from start to nth node, and what is h of n from nth node to goal node. Now, so we are starting with the H0. What is H0? Very trivial heuristic. Where we'll go? We'll optimize it and go to an optimal heuristic, which is H star. Okay, fine. Now we'll compare how changes is being happen if you go from H0 to H star. Means you are starting with the H0, you are going to optimal, you are going to more optimal, you are going to more optimal, finally you are reaching to, I should not say optimal, optimal is a single term. You are taking trivial one and you are going to better solution, finally you are going to optimal solution. So can we compare something? We can compare what is the cost of searching if you go to the optimality. So this is what is happening. If you are, increasing, you are making your heuristic to be optimal, means it is something give more, informed calculation. More calculation is there. Then the cost of searching increases. That's true. It is being increased. What happens with the computing heuristic? What happens with the searching with the heuristic? So if your heuristic is becoming more powerful, then what will happen? Cost of searching would be decreased, right? So computation cost increases because heuristic is becoming more meaningful, but search timing or the search, cost of searching would reduce because you are going towards optimal one. So it's like a trade-off. What trade-off? Do you need performance or computation? What do you need? If you need performance, your function should be optimal. Okay, fine, I'll give it optimal. If it is optimal, more likely the computation power will be high. And this is what it is saying. This is the trade-off. And if you consider both the information, cost of computing the heuristic, okay, I'll consider what is the cost of computing the heuristic, and also consider cost of searching with the heuristic. So if you consider both performance, as well as the cost, the graph would look like something like a blue. Means you are at very trivial heuristic. What is happening? If it were very trivial one heuristic, then the cost of computation is very less. That's cost of computation very less, but cost of searching is becoming very high because you are doing so much thing to reach to a solution because you don't have extra information, right? So that's what it is saying. So you can see the curve, which is like a bell curve, not bell curve, it is inverted bell curve. So if heuristic is very trivial, cost is going to high, but if you are going towards more better heuristic or the optimal one, computation increases. And this curve, if you see at the end, if it were getting very optimal solution, an optimal solution, not very then the cost of computation is becoming again high. So where is the optimal solution? Where does you should consider? So you see this marked one. This is where heuristic is good, better compared to H0, and also the cost is not costing too much. So if you have to see sustainable goal kind of thing, you need to consider both trade-off in account, then you can have something similar to this one. So what information you will have about this point? Let's see. Not always clear where total minimum occurs. This is something is not clear. Should we consider optimal function, or should we consider the performance part? It's not quite clear where is the total minimum occurs. Old wisdom was the global mean was closer to the cheaper heuristic. So it is saying old wisdom was the global mean. So where is the global mean? If you see this curve, blue one, global mean is at here, right? Was the closer to the cheaper heuristic. So this point, if you see this marked one, it is quite close to the cheaper heuristic. Cheaper heuristic means trivial heuristic. Trivial heuristic. Third point, it is saying current insights are that it may well be for cheaper heuristic for many problems. Pattern database of 8 puzzle or plan graph heuristic for planning. So these things we consider. Now let me summarize so what we discussed so far and what are the important point or how we will go further. So this graph is giving you the clear idea why heuristics are important. If you not consider heuristics, the cost of searching is too high. If you add the heuristic, cost become reduced, but computation increases over the time. That's okay. Nowadays computation is not a big deal. The big deal is it should get to the solution, and that too in less time. So cost of computing heuristic is more important here for this case, right? So it says this point clearly that when you are using something informed search, you consider the heuristic, you will consider it. It's more likely it will do better than whatever we have done till now. In uninformed one, where we don't have any information, we are exploring and finally going to the solution. But here we have some information, and that we are going to exploit it. Exploit in what form? In the knowledge form, that we are going to say that for the node, from that node going to from that node you have from that node to going to target node, for how much it is going to cost. So this is the heuristic function, what it represents. So okay, let's consider the h of n, which is from that node to go to g of n, g, what cost it is taking. But is it always good to consider only that information? Is it only good to how you are reaching the goal? No. What is the process you should also consider? What is the process? Process means for how you have reached to the nth goal. Is it a very difficult part? It's a very easy, or it's in between? If it is so, then you can have idea about that for reaching to from nth node to the goal is not only the criteria, but how we have reached the end goal, and that should also be considered, right? So it becomes a star equals to f of n, evaluation function to the each node is equivalent to h of n plus g of n. So g of n from start to n, h of n from n to target. So this is a kind of how we have learned about A star algorithm, right? Now before going in depth, if anyone have any concern, question and discussion point that needs to be discussed, please let me know. Then we'll go further and discuss about the questions about that we have to do some assignment question that we'll do. Okay, so let's go further and do some final assignment questions and see. So the first question, the most uninformed heuristic. So there are four options. H represents heuristic, H equals to 1, H equals to 0, or H equals to 2n plus 1, or all of them are uninformed heuristic. So think for a moment, and so it is saying there are few heuristics, right? Options are given. It is saying which one is the most uninformed, no information you are getting out of it. So it is asking which option is correct about that. So that you need to say. Yes, say what would be the solution for this question? The most uninformed heuristic. So if h is 1, you're adding something with g of n. If your function f of n equals to g of n plus h of n, so it is g of n plus 1, right? If I'm adding 0 to it, it is equivalent to g of n. We're not adding any information to that. It is becoming what it was, right? So are we able to give some information with this 0? No, we're not giving any information with that. H equals to 2n plus 1, then it would look like something f of n equals to g of n plus 2n plus 1, right? So finally we are giving some information with that 2n plus 1, that extra information we are giving. So which one is the most uninformed? Is h equals to 0. We are not giving any idea to the any intuition to the model. So which one will be most uninformed? Is h equals to 0. So this would be the solution. Now coming to the next question. With h equals to 0, let's assume h is 0. In last question discussed, which one is the uninformed? H equals to 0. If then how a star would act as? So our a star was f of n equals to g of n plus h of n. Now we are going to consider that h of n is 0 here. So you need to say how it would look like now, how it would act, whether it act as BFS, whether it's act as DFS, or whether it's act as uninformed causes or bidirectional one. So if h would be 0, then it is f of n would look like something like a g of n, right? What is g of n? G of n is same as cost search, right? So we are considering the path which is giving you the minimum cost. So here it would be act as in uninformed cost search. Answer would be uninformed cost search, right? Now next come to this question. Which of the following evaluation function, there are so many evaluation function, would emulate the behavior of greedy based first search? So we have few options, and which function we are going to use that is equivalent to greedy based first search. What is the greedy based first search? So greedy based search, we are saying we are going to select a node to be expanded which is more likely to reach the goal node in minimum cost. The cost from reaching to that node to the goal node is minimum compared to other node that can be expanded, right? So it is the definition of greedy based search. Now you need to select out of these four which options are going to emulate behavior of greedy based first search. So just understood whatever I said about the greedy based first search, think about that definition and try to see which one is going to make it like greedy based first search. What will be the solution? Which one is going to function make base first search? Let's understand it. First option is saying fn equals to g of n. What was the base greedy base first? It is saying I'll expand a node if heuristic evaluation would be minimum for that node. So there is no talk about g of n, how it has reached to nth node. It is not nowhere in, right? So we are only considering heuristic in greedy based first search. So wherever g of n is occurring, they are not going to be solution. So it's clear A and C is not going to solution. What solution would be? Only solution would be those who will be in form of h of n. So we are only going to consider heuristic. So the B would be correct if we are considering only the heuristic function for that nth node to reaching to the goal, how cost it is. If you just multiply with the 2, this is again the greedy base first search because the order would be same, right? Because you have multiplied every number with the 2, so it is same as the greedy base first search. So here the answer would be, what answer would be, where it is a function of h of n only, so it would be B and D. So right answer would be B and this one h of n and 2hn, right? Now let's go to any doubt, any question about that, so you can comment. Now going to next question. Which of the following graphs algorithm, there are few graph algorithms, are guaranteed to be complete and optimal? So there are graph algorithm, it is asking which are guaranteed to be complete and optimal. Complete means if solution exists, always the algorithm will give you. What is optimal? It will give you the solution which is optimal. Options are breadth first search, A star with zero heuristic. Zero heuristic means A star, how it A star look, it is Fn equals to Gn plus Hn. Here if they are saying heuristic is 0 means it is equivalent to Fn equals to Gfn. Third option is uniform cost search. So we discussed already about uniform cost search, right? A star with admissible heuristic. I'll run the A star, but with what? Admissible heuristic. Admissible heuristic means a heuristic which is always optimistic. Means whatever value it is saying, it is always less than or equivalent to optimal heuristic. So which one would be correct? These are the 4 algorithms. You say which one is always complete and optimal. Yeah, please someone say if you got it. Which of the following graph search algorithms are guaranteed to be complete and optimal? The answer would be for this question is uniform cost search, as you have already discussed in uninformed search, UCS. Uniform cost search is complete. If a solution exists, it will reach there, and it is always optimal. It will give you the solution which is costing you the minimum. If it A star with the zero heuristic, just we discussed, if you are using A star and that too with the heuristic 0, it is equivalent to your uninformed search. If H equals to 0, A star acts as false. It is BFS, DFS uninformed. It is uniform uninformed cost search. So that's why for this problem, the option B and C would be correct. Uniform cost search and A star with zero heuristic. Now come to the next question. There are two heuristics, H1 and H2, and both are admissible history. Then which of the following are guaranteed to be admissible? So two heuristics are there, H1 and H2. We are taking different combination of H1 and H2 for the new heuristic. If they were admissible, then which of the following were again admissible? Admissible means optimistic. Whatever it says, it should be less than. It should always be less than or equivalent to the true one. Now you just think for a moment and say which one would be correct. This is very important question. So you can consider also H1 and H2 as some function and do the calculation and finally come up with a solution that which one is again admissible. If they are H1 and H2 are admissible, then which of the combination of H1 and H2 would lead to admissible property. So let's understand. H1 and H2 are two admissible heuristic. Which of the following are guaranteed to be admissible? So which of their combination would lead to admissibility, would not lose the admissible property? So option A1 saying max of H1 and H2. If you'll take every time max out of H1 and H2, it would either H1 or H2, right? So both are admissible, then this would again lead to admissibility. Let's say I'm saying H3. So I'm saying this function, for example, so just a second. Yes, I was trying to write something on the slide. Sorry, but because of internet connectivity issue, I am not able to do it. So, so it is saying H1 H2 we have. Let's assume H3 is equivalent to max of H1 and H2. So every time you will get either H1 and H2 depending on their maximum, right? So either you get H1 and H2, it is admissible. So H3, which is equivalent to max of H1 and H3, again would be admissible. So option A would be correct. Now come to the option B, minimum of H1 comma H2. If there would not be plus 1, then minimum of H1 plus 2 again would be admissible because any of would come, either H1 or H2. But they have also put plus 1 here. So this property is being lost. If they'll plus H1, plus 1, it will either reach to H1. So it will be H1 plus 1 and sometimes it will be H2 plus 1. So it may not guarantee that from reaching to nth node to goal node, what previous value it was, if we'll add 1 to it, whether it will be again less than the optimal one or not. It may be greater than that one, right? Whatever the optimal we have. So putting 1 makes the trick here, and it will not be, we cannot guarantee it will be admissible. What about option C? It is square root of H1 and H2. You have two admissible property, you multiply it, fine. After multiplying, you make it square root. Okay, whether it will be admissible or not. If we'll do multiplication, we'll get a function h3, let's say, and we are doing a square root over it. So what it says, admissible property, it says only that it is always optimistic, means what value it will say, it is always less than real estate or equivalent to that one. So making h1 and h2 and taking a square root will be very much closer to what? If we will multiply two function h1 and h2, let's say 5 and I'm multiplying something 4, it is becoming 20. If you do square root, which will come again something closer to 4 point something. So what is happening? It is less than the maximum one. Yeah, so think about that. So h1 and h2, if I consider both are equal, then it will be h1 square and finally it is h1. So h1 would obviously be admissible. If they are not equal, then the number which we will get, it will always less than the maximum one, h1 out of h2, right? If it is less than that one, then obviously it will follow the admissibility property because it says the less than criteria and it is being followed here, right? So option A is correct, it will be admissible. Option B is, we cannot guarantee it will be admissible or not. Option C, we can see it is optimal, it is also admissible because there are two options, either they are equal or not. If they are equal, then you will get some like to the same number. If it was initially h1 was or h2 was admissible, then that number whatever will get out of square root is also admissible. If they are not equal, what does that mean? If they are not equal, if we multiply them and do a square root, the number which we will get, which will be less than the maximum out of these two. So maximum h2 was heuristic as it is given, then this number will also be heuristic, dh1 plus h2. If we'll do sum of it, no, we cannot guarantee the sum would be lead to the optimal admissibility, because if we'll do the sum, it was let's say 4 and 5 and there was a scenario for real world is 6 is less than 5, that's fine. 4 is less than 6, that's also fine. Both are satisfying individually. But if we'll do the plus, which is 4 plus 6 is 4 plus 5 is 9. 9 is not less than 6, right? So this property is being lost here. So what would be the solution for this question? Would be A and C. Maximum of h1 and h2 would be admissible, and square root of h1 and h2 would be admissible. We proved it how it is being happening here. So this thing you should do always when you get something, you try to reason about it, how it is happening. Now coming to the next question, this one is consider the following directed graph. Directed graph means you have given also direction. A as the starting node, G as the goal node, with the age cost as mentioned, age cost already mentioned here if you see, and the heuristic value for the each node is given here. H of A is 7, means from A to going to G you are going to get 7 cost. For B it is 5, B it is 6, and C 5 and all. So it is asking whether it is admissible and consistent or not. Just think for a moment and say. So when you have to check admissible property, how do you check? The definition you follow. The definition says whatever the H is given, you just see whether it is less than the realistic value or not. If it is always less than or even equivalent to the realistic value, then you can call it as admissible, otherwise not. So just check for few one and you'll get it. Yes, so for anyone, if you calculate, let's say if you have to see few options, so how are you going to decide whether it's admissible or not? So you just take a graph, it is saying A is the starting node and G as the goal node, fine. So we are starting from A and these are the heuristics given, correct? So you check the heuristic mentioned, for example some value, it is always less than equivalent to realistic node. H of A 7 it is given, right? So for if you calculate how much optimal cost is to go from A to G, so what is the optimal cost if you have to see? So if you calculate it, the seems like the optimal one be A C D E and G. Seems like so it cost would be or something else could also be possible. Let's see. So if I go through A to D through A B, it will be 5. If I'll go through C, it will be 4. So I am going to let's say C. From D to G, if I have to go, I can go like this, F through F, or we can go like 2 path through E and F and through E. So if I'll go through F, it will be 5. If I'll go through E, it will be again 5. If I'll go through EF, it will be again 5. So all 5. So 5, and here we are taking 4, which is 9, right? So it is all less than the real world. H of A is given 7, so it is following that property. It's just I give it example. You'll have to see for other as well. so that you can see and whether it's following. Given heuristic is admissible, yes, it is admissible, and whether it's consistent or not. What is the consistent definition, if you remember? So consistent definition was that if there exists path from a node to goal state and another path, right, then h of n, which is going directly to, let's say, goal, is less than or equivalent to cost it occurs the other path, c first is, then wherever you reach to that node to goal, that one sum. So you see this example. So for E, we are reaching G in one go, which is 4. Another way is going E to F, which is 1, plus F to G, right? So if you sum it, it is 4. 4 is less than equivalent to 4. Yes, it is. So yes, it is consistent. So this is the correct answer, right? Now coming to the next question. So you have to say true and false. It is saying all admissible heuristics are consistent. All consistent heuristics are admissible. Which one is correct? Think for a moment. So if you could recall, we discussed an important theorem which was saying if it is consistent heuristic, then it must be admissible. That follows. So first one is saying all admissible heuristic are consistent. No, it is not, because consistent is a superset of admissible, not reverse. So first one would be false and the second would be correct. So it will be false and true, which is B, right? Now coming to the next question. Which of the following will return an optimal solution in case of search graph has a negative is cost? So we haven't discussed about negative is cost, but which one will return to the optimal solution? These options are uniform cost search, graph search, A star with a consistent heuristic, both of these, or none of these. Think for a moment. So option 1 is the uniform cost search. No, it's not going to work. Yeah. With the negative is cost, but it just work, but not always optimal, because there is again a concept of negative cycle. Cycle and then negative loops, and also it is not going to work. Graph search A star with the consistent heuristic. No, it is also not going to work with the negative is cost for the optimality. So option would be none of this. No one is going to work for negative is cost for a always optimal solution. Now this is the problem. Consider the graph below. A is the starting node, B is the goal state. We perform depth first search branch and bound algorithm. Assume 0 heuristic with upper bound 6.5. So we are using depth first search but with branch and bound, and they have given a bound cost which is 6.5. If it is more than that, you are going to change the path. You are going to that. If there are any ties, then algorithm chooses to expand lexicographically smaller node. What does that mean? It means if you have option A of B and B,
with equal evolution, then you always select A because A appears first in alphabetical order compared to B. So saying also is we stop as soon as we reach to the goal. What is the first path predicted by the algorithm? So source is A, target is B, and branch and bound, upper bound is given 6.5. Now you have to say which path we are going to reach to the goal. Pretty easy question. If you just think for a moment, you will get it. So see, we have to go from A to B. That's okay. So there are paths going to A to D, and then another path going A to B directly, going A to E, and then B. Which one will take? So it's given already branch bound cost is 6.5. So we are not going to take A to B because there is already a path, but it is 7 and we have a bound of 6.5. Can we go A, D and C and then B? No, we cannot go because it is again crossing 6.5 because it is becoming 7. So we have only option. We can go A, B. Can we go A, B? It's 7. No, we cannot go. So we have only option A, B, C, B. A, E, C, B. So A to E is 3, E to C is 2, and C to B is 1. So 3, 2, 5 and 1, 6. So answer would be A, E, C, B. One extension with that, it is saying okay, not upper bound to 6.5, upper bound to 7.5. What will do? What will be the solution? If upper bound would be 7, then you see you have option of D, you have option of B, you have option of E, all those. So if you are reaching the goal in one go and branch bound is 7.5, no problem here. So you can directly reach to the goal because it is 7.5 and the cost is 7. So answer would be AB. Okay, so till we discuss there. If you have any question or comment, please let me know. We can discuss further about that.